Horizontal UCM. When a car goes around a curve, there must be a net force towards the center of the circle of which the curve is an arc. If the road is flat, that force is supplied by friction. If the frictional force is insufficient, the car will move more nearly in a straight line, as the skid marks show. As long as the tires do not slip, the friction is static. If the tires slip, the friction becomes kinetic, which is bad because kinetic friction is not as strong as static friction, and it opposes the direction of motion. Since the static friction force was perpendicular to the direction of motion, it is now difficult to maintain control of the car. We need two perspectives to analyze motion around a flat curve. On the left, we see the view from directly above a car circling the track with a velocity of v. On the right is the view of that car driving straight away from you. So it's as if you were standing on the road right behind the car watching it go. So here we have our top view and our rear view. Now we add the vector for centripetal acceleration to both drawings. So we have this A towards the center of the circle here, and here's the rear view of the car. Here are the tail lights, here are the wheels. It's going into the computer screen away from you, and the acceleration is towards the center of the circle to the right. The reason why this perspective is so important is that we can add the vertical and horizontal forces to it. The normal force and the weight are equal and opposite in the vertical axis, since there is no vertical acceleration. The force of friction is the only horizontal force, so it is the net force, and thus must point in the direction of acceleration, to the right. This free body diagram lets us solve for the relationship between the coefficient of static friction and the maximum velocity of the car on the track. Remember, we're dealing with static friction because that's going to help our tires grip the road and be able to turn. Kinetic friction would be opposing our motion. So we're dealing with static friction here so that we don't lose traction on the road. First, we begin in the y-axis to find the normal force. We have two forces in the y-axis, the normal force pointing up in the positive direction and mg pointing down in the negative direction. We don't have any acceleration up or down, therefore this is 0. When we solve for the normal force, we get that the normal force equals mg. Then we move to the x-axis. We have only one force in the x-axis, and that is static friction. So static friction equals ma. We can replace static friction with the formula for friction, which is mu Fn, the coefficient of static friction times the normal force, and we can replace a with v squared over r, since we're driving in a circle and we have centripetal acceleration. We solved for the normal force, it's mg, so we can go ahead and plug that in for the normal force. And then we can go ahead and cancel out those m's, giving us mu g equals v squared over r. Now we can choose what to solve for on the next page. Now we can solve for two things. We can solve for the maximum velocity for a given coefficient of static friction, or we can solve for the minimum coefficient of static friction for a given velocity. So here we would solve this for v, and we get Vmax equals the square root of mu gr. So all we've done is solve this for v. Over here, we've solved that same equation for mu, and that would give us the minimum coefficient needed to stay on the road at a certain velocity. Notice that the mass of the car is not a factor in determining either the maximum speed it can take a curve or the minimum needed coefficient of static friction.